thanks for the opportunity to give a talk. So today I'm going to be talking about this work that I did with Leonel Mazec and Sridhar Paul. And now there's also some work in progress with James Bonifacio, who also worked on something similar before, joined forces. And Leonel talked about this topic in a New York meeting. So hopefully not all of you were there, and that's going to be something new for someone. And also I'll just try to give maybe a different perspective from what, stress different things from what Leonel was doing. And also I think it's supposed to be kind of informal, so I hope you'll ask a lot of questions, and I will also simulate the informality by saying a lot of and so on. Okay, so in this talk, the main message that I want to try to get across is that in some sense you can define a set of correlation functions which you could in principle call something like maybe Euclidean conformal theory. And I just really made up this name for the purpose of this talk, but let's go with it. So, notably, this is not the same as CFT, and it doesn't have any field in it. So, to the person who will want to ask about stress tensors, there is no stress tensor. And I'll explain in a second what I mean by this, but more importantly, we think that there are at least few examples of this kind of structures which arise in things which are more or less familiar. So for example, we think that some CFTs, actual CFTs, so like 2D-izing, I'm pretty sure about this one, maybe 3D-izing, maybe all, I don't know. Give an example of the structure, then also, if I understood better what DSCFT is, I would maybe be able to be more certain about this, but quite possibly DSCFT gives an example of the structure, and which is more relevant to this talk, hyperbolic manifolds. So this is in d dimensions. Hyperbolic d+1 manifolds. Give an example of the structure. So, what I mean by this structure is basically a set of correlation functions in Euclidean space. So it's basically a set of correlators. Space which satisfy a bunch of properties. So they have conformal invariance, they have some positivity property which I'll call Euclidean unitarity. Which is not the same as reflection positivity for Lorentzian unitarity, and I'll explain what this is in a second. And we also have some notion of greater product expansion. So I'm not saying anything about whether they make physical sense or whether they, space makes some sense, or whether there's a stress tensor. I'm just saying it's a set of correlation functions which we find for some operators which are formally invariant, satisfy some unitarity condition, and satisfy some greater product expansion. Yes?
Sir, just to be sure, so is equivalent to reflection positivity?
It's not equivalent.
So it's
sorry, yeah.
rather equal. I'm confused.
It's not equivalent.
Okay.
Great. So not saying anything about the structure more than these things. But these things that you might expect are enough to do some kind of bootstrap because you have enough conformal symmetry, like some creative for expansion, unitarity gives you some positivity constraints, which you can then bootstrap.
Does this kind of theory appear in statistical physics or any other?
I mean, I'll explain what it is. It's not. I'm just using this fancy word to not get complaints that but does it have a stress tensor or what is the meaning of space-time? So I'm just saying that those separate things.
So this complex CFP that I think we studied in Numerical would be one example.
Sorry?
The complex CFPs, like the complex fixed points you find in our free flows, would that be one of the examples?
Complex CFPs.
Yes.
These are principal theories. It's not necessarily just come.
Well, he hasn't talked about that yet. Just within standard definition.
You mean complex CFPs like
Scaling dimension.
Yeah, for example.
I don't necessarily think that would be true.
But from what you have given so far.
Well, I'm concerned about.
So you want to define what you mean by equivalent?
Of course.
Okay.
And I think it's probably not going to be that.
Okay.
Euclidean, I understand. The problem I understand, why is it called theory?
God damn it, I knew that this thing was not good enough. Okay? Alright, so I'll change here. Now this really sounds like a kind of abbreviation that it probably means something bad, so I don't know. Okay, so what do I mean by this? I guess intuitively it's clear what conformal invariance is and OP is, and I'll go through this maybe in more detail, but the main point is this Euclidean unitarity. Euclidean unitarity is something that if you heard Sheen's talk a couple of weeks or two ago, I don't remember when it was, he called this squared positivity. So basically Euclidean unitarity in this context it's basically saying that if you have a correlator where you take absolute values square root of some observable, so this over could be a product of operators, not necessarily one operator, so this thing has to be non-negative. That's all there is to it, and let me explain why these things satisfy it. So if you take CFT, then when we compute some correlation function of this sort in CFT, and if you will ask questions, I'll maybe explain in more detail why this makes sense. So if we compute something like this in CFT, well, you might argue with me, but you can kind of be optimistic and you can imagine that there is some path integral which computes it. So we have path integral over some fields, path integral is over some space of field configuration is fine. We have some action, which depends on time. And then we have this observable that we're computing. And the whole idea is that, okay, well, you can ask whether this expression makes sense, but if it actually makes sense, that you would at least expect this factor to be non-negative. And this is non-negative by construction. So you expect the whole thing to be non-negative. So this, of course, assumes that I have some kind of safety. This is real action or something of this sort. So the way I want to look at this is that just I have some space over which I'm integrating stuff, and I have some kind of measure in this space, and this measure is non-negative. Any questions about this? The integral of non-negative quantities and non-negative quantities, so hopefully that's not too confusing. Now, if we take something like DSCFT, and now I should make a disclaimer that I understand nothing about DSCFT.
This model is quite, is it a subset to incident points?
Sorry?
You didn't define what a dagger is. You didn't define what conjugation is. So I'm just not sure I understand why it's not reflection positivity.
It's called what?
Why is this not reflection? Why is this not consequence of reflection positivity?
So an example of this would be, say, what you can do is you can take rotation value of which is so this was reflection positivity. I would have to tell you that F was supposed to be supported in some half plane, and then one of them would actually come with like F bar of X, for example, would come with X reflected along the plane. Here I'm not doing that. It's more like Lorentzian unitarity, but in Euclidean space in this sense. Okay. So at least if you forget all that you heard about path integrals not making sense and instant line singularities and so on, then this kind of is a statement that you might expect to hold. And the statement is that in some situations you can actually make sense of this statement, and this argument literally shows you that some things are good.
The answer could be infinite, though.
Sorry?
The answer could be infinite.
Well, in the cases when it makes sense, it's not infinite, it's finite. So for sigma field, it's actually finite, and you can check that it's positive. But the statement is, first, it's not just about 2-point functions, it's about multiplicative things as well. And that's what makes it
Sorry, how is that different from reflection?
So if you had, so the statement, for example, in 2D Ising is that this quantity is non-negative for any function f, which is smooth. And if you had reflection positivity, then the statement that you would have is that this f of this function f was only supposed to have support in one half plane, and one of these factors here would have f of x reflected across this half space, or you would have x reflected. There's no reflection in this formula. So naively, like the simplest thing that I might want to say is that just expectation value of sigma of 0 squared is non-negative, but that's infinity. So in order to make some kind of non-trivial statement, I'm smearing it with a test function. Take the square of that. So that is correct. Any other questions? Okay. So this is for CFTs, so that's why you might expect CFTs to have this kind of weird unitarity. For DS CFT, the idea is the same to the extent to which I would make sense with DS CFT, is that if you're computing something of the sort, then in a very kind of shallow level, you can think about computing expectation values as what you do is compute expectation values of some things which you insert at the future infinity in some state, so which is some Blanche Davis spectrum or whatever. And you can think about this in a similar way, so just the set of the action you have, this wave function squared, and then you have the same quantity. Since you expect these things to be non-negative, you expect the integrals to be non-negative. So it has the same structure, and this again you can call some d mu, which is non-negative. And the situation with hyperbolic manifolds is going to be the same, just that I will need to explain to you what is the space that you integrate over and what is the measure. It's the same kind of idea that the correlators in hyperbolic manifolds are going to be integrals of some space with some positive measure, and this will give it this notion of unitarity. Okay. So if this sounds good, then let me then talk a bit more about the CFT example, and then from there it will be easy to transition to this hyperbolic story. Just to stress this again, this what I'm discussing here is in some sense taking everything, like the Bootstrap axioms which we like, and then taking the usual unitarity which you might call the Lorentzian unitarity reflection positivity, just replacing it with this other notion of positivity. And CFTs have, well, unitary, what we call unitary CFTs have this Lorentzian unitarity, and as I said, maybe some CFTs have this Euclidean unitarity property. Now with this hyperbolic story, there is no Lorentzian unitarity, there is just this Euclidean unitarity. Okay, so let's look at this kind of expressions a bit in more detail. So imagine now computing some correlation function of some maybe local operators in the conformal field theory. And we again imagine having some path integral. And we have our local operator insertions. Integrating or some space of field configurations. So as I said, I want to think about these two factors as just defining some measure, and this is how mathematicians think about it when they actually are able to make sense out of path integrals. Now, what are these things? So in principle, this is kind of the shorthand notation. So if you look at one of the operator insertions, you should really think about it as some function of phi, which you just chose to label by this name of one of x1. So in principle, this function f 1 plus 1 is some function which takes us from the space of field configurations to the numbers. And of course, we ascribe some physical meaning to this local operator, so we think something about locality, etc. And another thing we know is that, okay, these things transform nicely under conformal transformation, but in principle, these are just some functions which we've decided are interesting and transform nicely. We are computing their kind of overlaps, so we're multiplying a bunch of them together and computing integrals. So this is how we kind of transition into this hyperbolic story, where we say, okay, at this level, the CFT for us is just some space over which we can integrate some measure, and conformal invariance here means that basically there is an action of conformal group on this space of field configurations, and the measure is invariant under this action. And then there is a bunch of functions on this space which we decided are interesting and they transform nicely. So what all we are doing is we're taking these functions, multiplying them together, computing integrals from these correlation functions, writing papers about it. So all we do to get to this hyperbolic bootstrap story is to replace this space phi by something simpler, and then come up with a new set of functions f that we would like to integrate.
Is there any problem with renormalization of operators? You write them all as just a plain function of the field.
Okay, so it seems like you want to get into this discussion. Yes, so if you actually try to make sense of this precisely, it's complicated because you're trying to make sense of the path integral. So that said, mathematicians have managed, or mathematical physicists have managed to make sense of a few path integrals. And when they do, as far as I understand, they don't really make sense of composite operators. So you have the fundamental field phi. So for example, you can take 2D theories with 2D scalar with some any polynomial interactions, and they can explain to you what the mu of phi is. And phi, this space over which you integrate, is a space of distributions in a plane. So there's so it's like some random distributions. And the functions that you can have are some phi smeared as a test function. So that they can make sense of. Now if you ask what phi squared is, I don't know that they have an answer. So if they have an answer, I don't know what it is. So in this sense, when I say that something like 2D-izing satisfies this, what I mean is that they actually make sense, people actually made sense out of 2D-izing correlators of sigma field as having some random distribution, some probability, with some measure phi, some measure d mu, and the correlators of sigma, which you treat as fundamental fields, can be computed by these formulas. So in this sense, you have just one primary operator that you can compute correlators of. And then if you want to make sense of something like epsilon, whatever, that I don't quite understand how to do that.
Okay, thanks.
And the difference with hyperbolic bootstrap is that in hyperbolic bootstrap you can actually kind of characterize the entire spectrum of things that you could possibly insert. Okay, so what we do to get to hyperbolic bootstrap is to say, okay, the first thing that we need is this space phi over which we're going to be integrating. And conformal invariance says that conformal group should act somehow in this space. So, and you know, if you have a space and you have a group action in it, then the space can be more or less complicated with respect to this group action. The simplest space would be something which is has a transitive group action, which means all the points in the space are the same. Now, in this space, this all look like quotients of our conformal group by some subgroup. So G here is the so 1 D plus 1, which is just a quotient by some subgroup. This quotient still has some right action by multiplication by G. So the elements which live in this space, you can write them as gamma G, and you can still multiply on the right by group elements to get new elements. So this is the space that we're going to work with, and what we also want is the space to have an invariant measure d. So of course, if we just take H to be trivial, so we'll have G, and then we have higher measure, and then if you want the quotient to have an invariant measure, you want this group to be so-called unimodular. And we mainly, so this works for any dimension. We mainly focused on d equals 1, although we are doing some work for higher dimensions as well. So for d equals 1, this is just SO1, 2 or PSO2R, you can actually go through the list of all unimodular subgroups and find out that most of them are extremely boring. And the only trivial example really is when this is a discrete subgroup gamma. Sorry, this here was supposed to be H, which I now have replaced by gamma. So the space is, so in d equals 1, this is pretty much the only interesting example. You can choose non-discrete gammas, you can choose some Lie subgroups of G, and then the whole story still works. You can just even choose G itself. It's just that it has much less structure. Somehow it's less non-trivial. You have some continuous spectrum, and that's it. Whereas when you have to choose some discrete gamma, you get something interesting that mathematicians actually care about. So bottom line is we choose our space to be a quotient of the conformal group by a discrete subgroup. And in particular, for simplicity, we also focus on the case when phi is compact space. What this means is that gamma has to be sufficiently large to quotient out all the infinite directions inside of the conformal group, so that we end up with a compact space. This is not the hyperbolic manifold yet. So the hyperbolic manifold you get when you take this phi and quotient it by SO d plus 1 on the right. So this is gamma G SO d plus 1. So this is actually the hyperbolic manifold. So in this sense, phi is like a hyperbolic manifold to which every point of which you have attached an SO d plus 1 group. Fancy way of saying this is that phi is the normal frame bundle of our hyperbolic manifold. And gamma here is the fundamental group of the manifold in this language. Any questions about this? Okay. So this defines the space phi, and you can check that it has a unique invariant measure, so the choice of measure is not a question. And this still doesn't tell us what to integrate over this space. So this is where I'm going to go next, how to define actual local operators in this scenario. So while I'm erasing, let me say that kind of one motivation for doing this is that, as I said, actual conformal field theories provide an example of the structure of this Euclidean conformal stuff, and also also, as I said, there are conformal bootstrap equations that you can write for this structure, and so conformal field theories are solutions to these equations. And these are highly non-trivial equations in principle. They're only different from the crossing equations is in the choice of positivity properties that you insist on. So the statement is then, turns out hyperbolic manifolds also solve the same equations. So I don't know, take this as an inspiration that maybe there is something interesting that you can come up for hyperbolic manifolds. Maybe there is some fancy path integral that you can write, which will localize in some phi, whatever. Or maybe you take this as a warning that, okay, maybe these equations are not so specific. So up to you, but that's the start.
So did we assume that the field theory was conformally invariant, that this measure d mu is invariant under SO1, b plus 1?
Yeah, that's the assumption.
And the statement that this form of phi is the most general one in this case, or this is just an example of the space-time?
So phi is not the space-time, phi is the space of field configurations. So it's like the space of different field profiles. That's where the path integral is taken over. Path integral is taken over the space of all field configurations. Right? It's like space of functions.
Then I'm probably confused. Why is such a small space?
And it satisfies the same properties, so that's what I'm saying. So conformal field theories presumably give an example of the structure of some extremely complicated space phi. Like in examples which we know about, like as I said, 2D-izing, space phi is the space of distributions on the plane, and there is some random measure of it. Here it's much simpler space, it's finite dimensional. This space here is infinite dimensional, it's finite dimensional, it's very small, but it satisfies all the same properties. As I said, all that you need is a space with a measure, which is invariant under conformal group action and some interesting functions on it. Turns out that this space has all that, so it solves this equation with a whole bunch of correlation functions. Maybe fewer correlation functions in the end than you could pull out of a CFT, but nevertheless, and so it gives us solutions to the same equations. So you can think about this as an example. Practical motivation for doing this is actually you can derive things about hyperbolic manifolds which we're not knowing before.
I don't know if this is correct thinking at all, but it seems that this space phi is a space of delta functions on your space-time. Imagine you have space-time which is a representation of your conformal group, and you have a delta function.
Yes.
Now you add the conformal group, you move the delta function around. That seems to be your phi.
It's a small phi.
Capital phi.
Yeah, well, this one.
Yes.
Yeah, I agree. But I guess you could think about it in this way. Why do you have to focus on things that just have one delta function? It's not clear. But we don't have to. All I'm saying is there is a structure that's an example of the structure that's also an example. One is much more complicated than the other.
But that's related to your comment, right? There could be some kind of two-dimensional field theory, and some localization mechanism where the path integral localized to this delta function configuration.
Yeah, that's the inspired optimistic point of view, and then there is a pessimistic point of view. It's like, okay, these equations are so dumb that we can't even tell like finite dimensional system apart. Okay, so how do we construct the correlation functions actually? So to construct the correlation functions, we need to choose some functions from phi to c. So we want to look at some space of functions in this G mod gamma. And when you have a space and you have a measure, one natural thing that you can consider is the space of square integral functions in it. So we can consider L2 of G mod gamma is our measure of mu. And in this context, the reason why it's an interesting space is because the space has a unitary, naturally has a unitary representation of our conformal group G. And the reason for this is just, of course, that if you have a function here, f of x, then you can define small g acting on f. Well, maybe I shouldn't call it f of x, let's call it gamma g. And we have some g prime acting on f, not compute at some point gamma g. Well, this is defined to be f of gamma g prime. You can check by variance of the measure, it just gives a unitary representation. And when you have a unitary representation, the first instinct is to decompose it into reducible representations. So, and indeed, if phi is compact, this decomposition is actually as a direct sum. So it's a discrete spectrum of representations in some sense. There is a unique trivial representation C, which corresponds to constant functions. Then there is a infinite sum over some subset of integers. So let me just write n an integer of dn plus d bar n, which are called discrete series representations. So discrete series representations are complex, so there is discrete series representation and its complex conjugate. And there is also a direct sum over all integers of some spaces C lambda k, which are what I call continuous series representations, which we'll explain. And I guess I'm not going to go into a lot of details on this, but the structure of this direct sum, it has one-to-one correspondence. It's in one-to-one correspondence with things that you can learn about hyperbolic manifolds. For example, these terms, discrete terms, correspond to some holomorphic objects that you can construct in a sorry. Let me say, at this point I'm just going to talk about d equals 1 case. Although you can also do this, everything for higher. So d equals 1 and hyperbolic 2 manifolds. Just for simplicity of discussion. So in higher dimensions, you will not have the discrete series terms, but the continuous series terms are going to be the same. So discrete series is special to 2 manifolds, and they correspond to some holomorphic objects that you can define on hyperbolic 2 manifolds, like holomorphic 1 forms, holomorphic quadratic differentials, and so on. And these terms correspond to Laplace eigenfunctions on the hyperbolic manifold. So just the fact, it's not hard to derive, I'm just not going to spend time on this.
So is for any gamma this decomposition on discrete for S2R, or
Sorry?
is for any gamma discrete the decomposition of discrete?
It is discrete if the quotient is compact. So if quotient is compact, then the gamma is called co-compact. So it is discrete for co-compact gamma.
No, I asked, is it known explicitly what it means?
What? Oh, but it's not explicitly.
Yeah,
So you can
physical function, yeah.
Oh, the discrete part you can compute by some knowing some, basically by knowing the topological type of the surface. It's like knowing the genus, and you can also allow orbifold points. So if you know the genus and the number of the types of orbifold points, you can compute the spectrum of discrete terms, but you cannot compute in general the Laplace spectrum, because it's just some short kind of triangular equation hyperbolic manifold. It has some spectrum, but it's not easily computable. And a lot of math literature is about studying this. And this eigenvalues, Laplace eigenvalues, they're linked to the quantum numbers of the operators that we can have in the structure. And so when you do bootstrap with the structure, you can put bounds on this eigenvalues.
The discrete ones also, can they be represented as eigenfunctions of the Laplacian?
Well, so Laplacian in terms of the Casimir operators here. So yeah, I mean, every representation is an eigenfunction. To be clear, so this holomorphic objects correspond to like lowest weight vectors here and highest weight vectors here, and then Laplace eigenvalues correspond to like zero weight vectors here. And these spaces have much more vectors in them than just one. And these other vectors are just derivatives of these objects over the surface.
Here, each representation comes with multiplicity 1, or could it be, depending on gamma, could it be?
Yeah, it could have multiplicities. Some surfaces have isometry. So, for example, it would organize also in the representations of isometry group.
So if I don't quotient by gamma, then the space decomposes into many more representations.
Yeah, if you don't quotient by gamma, first you would have something that's not compact.
Yeah.
So you'll have still this discrete series. Well, it's the regular representation of compact Lie groups. Regular representation just has left and right representation, so I can close this like
All
all
the
the
space of
representations.
matrix elements.
Sorry?
It's just the space of matrix elements?
Yeah. You have to, it's like it's slightly more different because you have this continuous spectrum of the continuous series representations. So it has like delta normalizable stuff in it. Okay. So how can we use this to define these interesting functions? So the idea for this is that it turns out that technically it's more convenient to rephrase slightly what having this decomposition means. So let's say there's some particular continuous series representation which appears in this direct sum. Wait, here I was actually not careful. I wrote the equals, but it's actually, I have to be careful and say that this is isomorphic. And having a particular term appear here means that I can find the map, I can call tau, from this term, so let's say C1 decay into this L2 space. I can take that, I can make my favorite model of this representation, and I can insert vectors from this model into this space, and I'll get functions in Gmod gamma. Right? And then the idea is that I can find some things which I'll call O of x, which I think are nice inside this standard kind of model of representation that I prefer. And then I can make functions in Gmod gamma by just applying tau to this, to my favorite elements of the representations. And Schur's lemma guarantees that basically tau is unique up to an overall constant. So choosing tau is in a sense like choosing a primary operator in the theory, and Schur's lemma guarantees that the choice is unique up to, like, assuming, for example, there are no degeneracies, so in generic case, choice of this map is unique up to a constant multiple. So in particular, if I explain what x is, just referring to the representation, I also explain what x means for my surface, just thanks to Schur's lemma. It doesn't give any physical meaning to this variable x. It just says that, well, maybe it has physical meaning, maybe not. I just don't need to know it in order to define what these objects are. Now, perhaps if there is some fancy theory which localizes on this integral, there is some meaning to this x. But in order to find correlation functions, we don't need to understand it. And we don't understand it, so that's good for us that we don't need it.
If there are multiplicities, then this tau is not.
Yeah, but that's the same. When there are multiplicities, like choosing the basis of tau is basically choosing a basis of local operator. Okay, so how do we define this object? So for this I should probably tell you what is a continuous series representation. And continuous series representation is just a name that I use for the set which includes principal and complementary series. And complementary series, you should think about it as just a weird version of principal series, which you have to deal with if you want to work with deltas which are not complex, but just in a small window in real life. I'll just focus on the principal series for now. So principal series representations. So lambda is basically I label it by delta, where delta is related to lambda by this formula. So lambda is basically the Casimir of the delta, is a minus sign. So it just consists of square integral functions on the real line. And if you want to take a function and apply to it some conformal transformation g, and ask what this new function is, then it transforms like a primary operator with shadow dimension. So it has some scaling factor to the power 1 minus delta, and the function itself is transformed in the standard plane. So I'm not writing out this explicitly, but you should think about this the same. Transforms as primary operator, the same formula, just this delta replaced by 1 minus delta. And the inner product is just whatever there is on L2, so absolute integral of absolute value squared. And that turns out to be a nice unitary representation, which is also irreducible. And it's unitary when delta is in this 1/2 plus omega 1, which is all principal series. Delta is on the principal series. Now, these are some explicit functions. So, for example, if I want to specify elements of it, I can take, say, that e to the minus x squared is an element of this representation. And I want something which looks more like a primary operator. So I need to define for every x what function corresponds to all of x. So in this sense, the informal definition would be that all of x, which now needs to be a function, so y is going to be delta of x minus y. So this is an informal definition. Formally, what I'm defining is I'm saying, well, I'm not going to tell you what all of x is, I'm going to tell you what integral of all of x or dx is some test function is. And this is just going to be f. And so this is so too. And then you can check that all of x transforms as a primary operator as dimension delta. Because f in this integral transforms as dimension 1 minus delta. And it's an interesting subtlety which will come up in a second, that I actually want to think about this all. I don't want to allow f to be any functions. In principle, I can allow f here to be any square integrable function, because then this integral by definition just produces the square integrable functions that inside of this L2. What I want to say that I will allow this for smooth functions, which decay quickly. And the reason for this will become clear in a moment. Then I can talk about all of x as a distribution valued inside of this principal series representation. And then when I take tau of all of x, I get the distribution which is valued inside here. And the reason why I wanted to restrict to smooth functions f is that if I took just square integral function f of x here, then I would only guarantee that I end up in this space after I apply tau. But it turns out, for a rather subtle reason, it's not obvious at all. If you restrict f to be smooth here, you can prove that you will get not just square integral, but you will get a smooth function in this space. And this follows just from representation theory, but it's like the kind of representation theory which we physicists never talk about. Okay. So the bottom line is, when we have representations appearing here, we can define special elements inside of these representations, which you can call primary operators, and by inserting them into this decomposition, we get some functions in G mod gamma. And if we are smart enough, we can ensure that these functions in G mod gamma are actually smooth and not just square integrable. And these functions labeled by our favorite weight letters all of x, and x maybe has some meaning, maybe it don't. We don't need to know this meaning in order to define this object. So let's do a summary. Okay, any questions so far? Okay, and now we can finally define the correlation functions. And this is where taking smooth functions was important. Well, not necessarily smooth, but where taking square integral functions is not enough. It's because we want to define a correlation function. So let me call this object. Let's like this. So we can now define correlation functions. The integral over our space, which is G mod gamma, is the invariant measure, which I'm just normalizing so that this itself is 1, and then I insert some functions which we just instructed. So if I'm being very explicit, then each of these things is a function of phi. And the reason why I wanted to be careful not to get square integrable functions here was that if I just knew that this O of x1 is a square integrable function, then I wouldn't be able to take product of n of them and say that the integral of this is finite. I could take 2 of them and say the integral is finite, but not like 3 or 4 or more, which is really what I want to do. But if I know that the function is smooth, then I can do this. And again, here, these are not actually functions, these are function value distribution, so this formula should understand after taking the integral with some test functions over x1 and so on, xn. And I'm being here very pedantic about this distribution thing, but it has a, it's going to come back in a second, so there is a reason for this. Any questions about the definition of the correlator? So these things are that we defined conformally invariant by construction basically, because everything that we did was behaving nicely with respect to conformal group. They also satisfy positivity simply because it's an integral of stuff with positive measure.
Sorry, can you explain? I got this. What can you explain again what this what was tau? I think lost some stuff.
So tau. So I have this space,
Yes.
and if I ask how does it look in terms of irreducible representations, it has some decomposition. Right? But what is a representation of the group? It's like a vector space on which it acts, in which the group acts, and then other words that we say in that situation. But that vector space, when I tell you like principal series representations, C delta, it's like some square integral functions on the line, etc. Right? It doesn't mean that this space literally appears inside here. It's a different space. They don't have anything to do in common. What I really mean is that there is a map which allows me to take these things and find corresponding objects inside of this space. And tau is this map. Tau is like an isomorphism of between the two. Because the difference between these two spaces, between this space and this space, is that this space I understand and I can write concrete functions here, like e to the minus x squared is a concrete function. It's a concrete vector in this space, but I don't know how to write down the concrete vector in here. So what I'm doing instead is I'm saying, okay, well, this representation appears in the sum, which means that there is a map which allows me to translate that object into here. Okay?
Yeah.
So do we know the lambda k's, or do we want to find them?
Lambda k's exist.
Given gamma, do we know the lambda? Do we know if I give you some gamma, would you be able to tell me the lambda k?
It's kind of like given a differential operator denotes spectrum. Like it's the same kind of problem. You can put it on a computer and get numbers out, and but in principle, there is no formula except in like some very obscure cases. So I don't know when phi is compact. I don't know a single example when there is a formula.
But okay, so then if we don't know the closed form for the lambda k's, do we know tau?
Tau.
Yeah.
So knowing tau would amount to knowing actual eigenfunctions, because you can plug in a particular vector which has zero charge under SO2 inside of tau, and that would produce for you the eigenfunction Laplace operator in the surface. If you knew the eigenfunction, then you'd be able to apply that Laplace operator and compute the
But we
values.
don't know either lambda k or tau.
Yeah.
Can you explain again how the matter is defined? This d mu phi?
Sorry? How the measure
Can
is
you
defined?
explain again how this matter is defined? D mu phi.
Yeah. This one is easy because so there's hard measure on the group G, right? And I'm taking quotient by a discrete subgroup. So locally, G1 gamma looks like G. So it's just the same as higher measure, just transported onto this quotient. You can also take quotients by things which are not discrete subgroups, but like actually like at least one-dimensional Lie subgroups. And then mu still exists if the subgroup is mini-modular, but then they will have some slightly more complicated description. Okay, so the last thing I wanted to explain is the creative product expansion, which is, if you think about it, I mean, every time I think about it in this context, it sounds extremely stupid, but that's what it is. So creative product expansion is just literally taking two functions and multiplying them together and getting a new function. It's just that now we want to break this new function down and further to this decomposition. That's all that the creative product expansion is in this situation. So if I take something like O of x1, O of x2, and again, should mention that I'm smearing x1 and x2 with some test functions, then this is a smooth function on G mod gamma, because just two smooth functions and multiplying them together, and G mod gamma is compact by our assumption, so it's a square integrable function. So this is some new element of this L2. So G mod gamma. And what we can do is we can just project it now term by term onto each of the components here. Now, this by itself doesn't sound very exciting because somehow I need to take into account, like the exciting thing about the being conformal theories is that it's so constrained that I just need one number to describe it. So how do I see this number appear here? And I guess when I first started thinking about this, to me the most kind of my intuition was, okay, let's take tensor product of two representations. That's going to be something to do with this tensor product. It turns out it's, again, it's the physicist being naive, thinking that there's just one tensor product and infinite dimensional spaces is the same as finite dimensional spaces. So it's not actually what you need to do. So taking tensor product is not what you need to do. For example, if you take tensor product of two principal series representation with itself, this tensor product doesn't have the trivial representation inside of it. But you still want to have a two-point function. So this turns out to be relatively subtle, and I can tell you about it offline, but the correct logic to pursue here is that in addition to this maps tau that we have that take us from some standard representations inside of this L2 G gamma, so we have this tau, there is also a map which takes us from it projecting into any of these components which we call phi. Let's say projecting here. So what we can then do is we can take, instead of thinking about these objects directly, we can also just think about taking tau some vector psi1 inside of our representation, taking some vector psi2 inside of our representation, and then applying projection onto some reducible component. Here, for example, and some other continuous series representation. And what this constructs for you, this object itself, is a map from our C lambda, say C lambda 1 times C lambda 2 into C lambda 3. So these are the kind of things that you need to look at. And then it turns out that the conformal invariance constrains such maps so severely that actually the space of them is one-dimensional. So you can say that this is some constant C times some standard expression. Yes?
How do we know the product of two functions to L2?
It's not. So that's why I was saying that I made sure to check that these things are actually smooth functions. That's why I was insisting on it.
So even if they are smooth, still not there.
Well, the space is compact, so product of two smooth functions and the coupled space is L2 integrable. Product of two smooth functions is smooth, and the smooth function in compact space is square integrable. So if you want to be super precise, then here you actually need to put distance, which is the space of smooth vectors of representations, and then that's the thing you actually study.
How do you choose lambda 3?
So it can be anything. So you just take a product and then you look at projections in every term, and then you can reconstruct the product back by adding everything up. The point is that you know the form of the projection on every single term up to just one multiple. So it's the same story as in CFTs.
This would be multiplicity again.
Yes, and then you deal with them in exactly the same way as you deal with them in CFTs. So this was maybe a bit too abstract, but the bottom line is that you can still write the same OPE formulas after you go through the math. So for example, here, what it will end up being is that for example, contribution from principal series terms will look like there's some discrete series and then sum over k, sum of p coefficient, or now we can call it c k. There's going to be some kernel, which is essentially some integral kernel, some standard thing which looks like a 3-point function times integrated over dx naught times this OK x naught. So you can just write formulas like this, and there are some of the coefficients k which appear, and the rest is fixed by conformal symmetry. And ck you can identify with basically integrals over the hyperbolic manifold of Laplace eigenfunctions. So we have so the interpretation of this p coefficients is that you compute your Laplace eigenfunctions, you multiply them together, and you integrate and you get a number. That's what the p coefficient is. In our paper, we focused more on the left-hand side. We didn't actually put the principal series representations because for technical reasons it was more convenient to put discrete series representations here, for which you can define similar operator-like objects, and then the OPE still works. And then you can use the OPE to compute 4-point functions, post-crossing, and so on. And the interesting thing about, for example, 4-point functions of these principal series operators is that it's conformal block decomposition, so to speak, is what we normally call conformal partial wave decomposition. It's the sum over principal series and block plus shadow block. That's literally the same expression. And the unitarity in this case is that the weights that you have along the principal series are non-negative. And normally in CFT we would have an integral over principal series, and here, because the spectrum is discrete, we just have a sum over discrete points on the principal series.
Sorry, Peter, I didn't understand the previous statement you made about identity not appearing in the OPE of the principal series.
It appears in the OP. It doesn't appear inside of the tensor product, so that's what I was saying.
No, but like in the Duvio, this is exactly what happens when you fuse the momentum operators above the threshold, right? Identity doesn't appear. Why is that a problem?
I mean, it's not a problem per se. It's just that here it actually appears in the sum, but it doesn't appear in the tensor product. So the tensor product is not the right thing to do.
But this mathematical subtlety that you were hinting at somehow didn't matter for the Duvio?
Well, Liouville is not in this framework. So
You're saying that correlation functions are not defined this way. So
yeah.
So what this means is that I can't think of going from the second line to the third line by just further multiplying by OK and then looking at the coefficient of the identity.
Oh, this you can do.
But how is that consistent with the fact that the identity doesn't appear?
Identity appears here, so there is identity here. What I will say is that naively, when looking at this thing, okay, maybe just forget about that comment. It's like the first thing that we try to do to understand what is the mathematical structure which describes this OPE kernels here. We thought about tensor products. Turns out that's wrong. The reason, and seeing that it's wrong, one way to see it is to think about identity. If this idea didn't come to your mind, you don't have to think about the reason why it's wrong.
Yeah, but I'm not worried about the identity appearing in that product. I'm worried about the identity appearing so when I take a further product with OK, then from the OK piece, whether I have the identity.
Yeah, you will have that.
You will.
Yeah. Just forget my comment about it. Everything will work as you expect it to work.
I forgot it already.
Okay, so
Sorry, but the integral in the third line is over the plane divided, hyperbolic plane divided by that.
no. So this x, as I said, so this x lives just on the real line. It's like this imaginary variable which I introduced when I was describing to you what the principal series representation is abstractly. So this is that x here and here and also here. So this x is integrated just over the real line.
That's why does it square, why does it take this square?
Sorry? Sorry, which x? Here or here?
The third line,
This,
There's a dx squared.
so this guy is integrated over, this guy is integrated over the hyperbolic manifold, which is G mod gamma, but also Gaussian SO2.
Yeah, exactly, this will come here. And can you comment just why this is?
That's kind of what Sue was saying. You can compute the coefficients here by multiplying by this guy and taking the expectation value. And then this expectation value is like a 3-point function, which comes with this coefficient. And then if you integrate over x1 as a specific weight, so you can choose weight, which is like 1 over 1 plus x1 squared or something of this form. So if you integrate over this coordinates with specific weight, what you will produce is SO invariant vectors in your representations. So the whole expectation value will then kind of descend. So this integral here, you will be able, because I should say it this way. So imagine there are 3 of these things here. You integrate with respect to x1 in a special way. Each of them is a special chosen test function, which makes this function here not depend on the coordinate along SO2. So everything that you get is 2 pi times an integral of some functions over the hyperbolic manifold. And these functions turn out to be the Laplace eigenfunctions, which is a consequence of Casimir operator. So then it turns into this expression. It's not immediately clear. I'm just telling you that the interpretation is it's all triple overlaps of Laplace eigenfunctions is this. Okay, I think I'm pretty much out of time. I could say a few more things about the kind of mathematical results about hyperbolic manifolds that we get out of it. But the basic idea is that now that we have this setup, we can do Bootstrap with it, which is slightly modified from the usual Bootstrap because it's on the principal series and so on. And then we get bounds in this lambda case, which turn out to be very close to being saturated by various two-dimensional hyperbolic manifolds, and we are also working to extend the story to higher dimensional hyperbolic manifolds, although that is more complicated for various reasons.
Do mathematicians also care about bounds on the OP coefficients? Or?
Yeah, thanks. That's actually one thing that I wanted to say. Yeah, they care about the bounds on the OP coefficients. It's connected to some fancy hypothesis in some obscure way. They actually have, for example, a theorem which bounds this OP coefficients as k goes to infinity. And you could say, okay, how does this compare to, how does this bound compare to what I need for like the partial wave expansion of 4-point function to converge? And then you can check, and it turns out that what their theorem guarantees you is that the partial wave expansion of 4-point function converges, but only as a distribution. It doesn't guarantee you that it's a function, that the sum is a function. It can only guarantee you that the sum is a distribution. Maybe it's still a function, but you cannot conclude that from their bound to their peak coefficients. And this is why I was so careful to say that we can only define this object as a distribution, because we don't know either whether it's a function or a distribution. The only way we can define it like once we get to this number, we only can say that it's a distribution of x1 through x4, and that's consistent with what coefficients bounds and this overlaps can tell us. But you can do also, so coefficients also say the Tauberian theorems for this crossing symmetry in very different language, but we think that's what they do. And we're trying to see if something else can be said about this. Oh, I know, I could go on for more, or I can stop here. I think it's a good place to stop. So.
Could you say something brief about the results?
Okay. So what we do actually is slightly different. So here I was talking about principal series only, just because it's just to save time. But in the end, if you do the same exercise about constructing these operators also for discrete series, what you find is that discrete series operators, they're in some sense more like what we're used to in CTs, but let me draw this picture. So imagine Riemann's here. So and this is kind of the real line. So this is leaving R. Then these operators that we just constructed, they live here. We can also construct the operators corresponding to these terms, which turn out to live from these hemispheres. So we have O here and O bar here. And they also have their own OP and so on. The difference is that, for example, if you take two discrete series guys and take their OP, you can take it kind of for this. I mean, that's just a picture. Really, it comes out from like some actual calculation. But if you take the OP of these two guys, it can only produce the guys which again live here. You take the OP of these guys, they produce the guys which live here. To take the OP between them, then everything can appear. And what we do is we look at 4-point functions, these two discrete and two discrete conjugate operators. And there are two channels. One channel is this, when only discrete terms appear, discrete series terms. And another channel is this mixed channel, where principal series appear. And the discrete series representations, they labeled with this integer n. And before you bootstrap something, this 4-point function, you should ask, well, does my manifold actually, hyperbolic manifold actually does my manifold actually have this particular discrete series in it? And then you can actually, this is something that's given gamma is easy to compute using Riemann-Roch formula. So you can know which ends appear here very easily and run this hard. So in this sense, what we have is a nice structure where one channel contains things which are easy and the other channel contains things which are hard. That said, the OP coefficients in the nice channel are still hard, so we don't know them. But we know what appears, and we can put things on the outside. In particular, we can, by just staring at Riemann-Roch formula, we can prove that on any hyperbolic to manifold, in fact, we have to consider not just to manifolds, but also to orbifolds. On any of them, like the smallest n that appears is either 6, 5, 3, or 2, or something of this sort. So there is a finite list of 1. There is a finite list of options of n, for which you know that at least one of them appears in any hyperbolic to orbifold. And then we just bootstrap the 4-point functions for all of them. And we put the bound, for example, what is the largest allowed gap in the first, lambda 1. And for this question, we get, it's a very concrete question, the answer is just a number. Right? And so you get the answer that in any hyperbolic to orbifold, lambda 1 is bounded by 34.88. Not going to remember. 35. We get more digits. Then you can ask, well, what is the largest number one that is known? And the largest one that is known is lambda 1 max is 44, 835, 37, and then you cannot compute it to higher precision because of the suck at computing Laplace eigenvalues. So, as far as you can tell, it is saturated, but whether it's actually saturated, you have to work harder to compute the eigenvalue. On the one, we know much conditions for the bound. And this appears for, so this turns out to be for hyperbolic manifold, which looks like basically a sphere with 3 fundamental singularities. One for the 2, one for the 3, and one for the 7.
This lambda 1 max, is it known analytically?
No.
There are two, both are numerical calculations.
So here we have a numerical calculation, but I should say that for once we actually, so what we did was we ran as the PB to get this high precision numbers, and then we rationalized them, and then we checked using rational arithmetic that these numbers actually produce a valid functional. So we have like an exact rational number, which gives us a bound which we know is rigorously true. We could make this number maybe a bit smaller, but it's exact in that sense. And this number is just an approximate number which we get by just numerically solving the Laplace equation. And we're not very good at it. There are people who are much better at it. And they tell us.
Is there a lower bound from like variational method?
Sorry?
Is there a lower bound from like variational method?
Lower bound on what?
Well, you put some ondas, you do variation, and I assume you can bound the energy from lower.
For a particular surface.
Yeah.
Well, yes, presumably. I mean, this is lambda 1 max for a particular surface. I mean, it's,
This you solve the Laplace equation.
Yeah. Well, okay. My statement is simply that with the amount of work that we were willing to put into this number, this is the precision with which we know it, and we haven't tried to get it back. There are people who can do much better than this. On the surface, there are, like, for things which the physicians are just not very interested in this particular orbifold, and things that they're interested in, they have, like, hundreds of digits. So it's not that kind of thing, it's just that we don't know how to get that precision.
And from the can you use the extremal functional method to figure out the second eigenvalue, compare that with the second eigenvalue on this surface?
Yes, so you can extract and you get some numbers, which I don't have at the moment, but you can find them in our paper, and they coincide pretty much with the eigenvalues. So there is they skip one low eigenvalue because of some isometry. Or symmetry or something of this sort.
So that's additional evidence that separates the surface vectors to that.
They're kind of, the precision gets worse as you get higher in eigenvalues, and it's not clear, if you crank it higher up, whether it will actually get very precise or not. It's not something that we have predicted. But it roughly reproduces to, where roughly I mean like sub-percent level.
You mentioned that the saturating surface has the symmetry. So can you see evidence of the symmetry from your Bootstrap analysis?
It has a Z2 symmetry, Z2 isometry, and I think
That's not the
that's missed as Z2 odd or something like this. So there's like an eigenvalue which it has, which doesn't appear in the external function, and that I think is for symmetries, and there's a bunch of other things that we do. That's the most basic result.
Okay.
I guess we are pretty much out of time.
Okay.
Should thank Petr.